Here's a practice SAT question. It involves a system of linear inequalities. Each of the inequalities involves two variables, y and x. So in order to get a graph, we're going to have to use the coordinate plane. That's already kind of implied by what they showed us above the problem statement. They showed us an x-axis and a y-axis with the four quadrants being labeled. And it says if the system of inequalities is graphed in this plane, which quadrant contains no solutions to the system? So it should hopefully make a lot of sense that if you actually try to graph that solution, you're going to end up being able to develop the answer without too much effort once that's done, as long as it's done properly. So I chose to graph this first inequality in blue. So if I think about this as an equal sign, I end up with y equals 2x plus 1. So I have a y-intercept of 1. I have a rise of 2, a run of 2, right? So y-intercept of 1, slope of positive 2. I have a solid boundary there because the equal to portion is included with that inequality, and that's how we indicate that the boundary is included with a solid boundary as opposed to a dashed boundary. Whenever we graph this one, we kind of do the same thing. Think of this as an equal sign and graph y equals 1 half x minus 1. So the y-intercept is going to be negative 1. The slope is going to still be positive, but it's not going to be as steep as this, right? We're going from a slope of 2 for that blue boundary to a slope of 1 half for this boundary. So I do a rise of 1, run of 2, which gives me a more level line. What I'm trying to do is I'm trying to see where the region is that overlaps between the solutions to both individual inequalities. So as long as your inequalities are in slope-intercept form, if it's a greater than inequality symbol, you're going to shade above the boundary. If it's a less than inequality symbol, you're going to shade below the boundary. The other way you can try to decide where to shade is you can pick test values. That's usually what I like to do, just because there's no guesswork as far as getting into the slope intercept form, possibly forgetting about to flip the inequality symbol if that was something you had to do. Again, not an issue here. These were already presented in slope intercept form. So using that trick I just mentioned, if it's in slope intercept form, greater than we shade above, less than we shade below. That works in this case. But if you wanted to pick a test value, like for the blue boundary, 0, 0 is clearly below that boundary. If I put 0 here and I put 0 here, so 0 in for y, 0 in for x, I get 0 is greater than 0 plus 1. Well, 0 is not greater than 0 plus 1, and that means relative to the blue boundary, 0, 0 must not be in the shaded region. Therefore, I would shade on the other side of that boundary, right? One side or the other side of this blue boundary is going to end up working. We've just determined it's not the underside, therefore we shade the upper side. We can do the same thing for the red boundary. Now, 0, 0 is above the red boundary. If I put 0, 0 in place of the x and the y in this inequality, 0 goes here, 0 goes here. I get 0 is greater than 0 minus 1. Is 0 greater than 0 minus 1? Yeah, for sure. Relative to the red boundary, 0, 0 is above it. It worked when we plugged it in, and that must mean it's in the shaded region individually for the red boundary. So I'm going to be shading above the blue boundary. I've indicated that with the little directional arrows here. I'm also shading above the red boundary. Where do the two shaded regions overlap? Well, that's up in this region here where you see it's highlighted. So hopefully you kind of understand why I have the region that's highlighted. That is the solution to the system. The question is, which quadrant contains no solutions to the system? So which quadrant is the one that doesn't have any shading within it? The shaded section is the solution set. The quadrant without any shading is pretty clearly quadrant 4.